All right. For section day 2 of 12.2, we are going to talk about algebraically determining limits at infinity. So these will be the ones where it's saying x is going to negative infinity or x is going to positive infinity. And I know that these are typically the hardest ones to conceptualize, so I'll do my best to really clear that up, try to make it as clear as possible. So first thing, this is going back from chapter 2 at the beginning of the year, is a review of end behavior, talking about does my polynomial function, so no fractions, we're just dealing with polynomials, what is the degree, what is the lead coefficient positive? So for the first one, if it is an odd function with positive lead coefficient, remember the ends are going to end going opposite directions. So the limit as x goes to negative infinity will go to negative infinity. As x goes to positive infinity, the function is growing upwards, so it's going to positive infinity. Let's go to the other odd one. If we have an odd degree but a negative lead coefficient, it flips it. So remember, if it's odd, they're doing different things. One is negative, one is positive, but now they're switched. As x goes to negative infinity, that graph is going upwards to positive. As we go to positive infinity, that graph is going downwards to negative infinity. For the even degree, this is where the ends end either going both up or both down. So in this case, if it is a positive, even degree positive lead, both arrows end pointing upwards towards positive infinity. So as we go to the left or the right, the graph is going to positive infinity. With an even degree and a negative lead coefficient, we are going downwards, negative, negative. All right, so then let's look at what this looks like for these limits. So the limit as x goes to infinity of negative 2x to the fifth minus x to the fourth plus 1. What we want to think about is the lead coefficient. It is a negative odd. For negative odd, that means that on the left it's going up and it ends going downwards. And so then this would go, as x goes to negative infinity, this would start going toward positive infinity. It's opposite of what we think. That's going to be this one right here. So it would look something like this. All right, let's do the next one. Number 2, limit as x goes to positive infinity. Looking at my lead coefficient, it is a positive number and it is an even. So those are the ones where our arrows, doesn't matter what it does in between, but our arrows both end going up. So as we look positive infinity, that's the right arrow. It's going upwards. So that's positive infinity. Next up, for number 3, we have our lead coefficient is negative, and the degree of this function is even. So for a negative even, they both end going the same direction. So this would be going down to negative infinity. That would be this guy over here. And then lastly, for the last one, they did not put it in order here. So we want to look for our term with the highest degree. That's 4x to the third power. So this is positive and it's odd. So as x goes to positive infinity, my arrows start down, they end going up. So as we go to positive infinity, it would also be going up toward positive infinity. All right, so one important note to remember is that these limits do not actually exist, but we are describing the end behavior of the graph. So if it's not a number, it's not actually a limit that exists, but we're using infinity to describe direction and behavior to tell us about this graph. So limits can give us specific values, but limits can also tell us general trends and behaviors. All right, so those are limits of polynomial functions. We're going to use, so for if it is a polynomial, if there are no fractions, if all of the exponents are whole numbers, we're going to use the end behavior summary to calculate this. When we work with a rational function, remember that that is some sort of fraction where our function f of x has some polynomial numerator and some polynomial denominator. This is where we talk about top heavy, bottom heavy, or equal. And this is where we have horizontal asymptotes. So let's use these rules to go back and review. If the degree of the numerator is less than the degree of the denominator, this is bottom heavy. If it's bottom heavy, then it has an asymptote at y equals 0, and that will come into play here importantly for our end behavior. If the degree of the numerator is equal to the degree of the denominator, so this is when we call them equal, then our horizontal asymptote is going to be the ratio of the lead coefficient of the numerator divided by the lead coefficient of the denominator. And then lastly, if it is top heavy, the numerator degree is greater than the denominator degree, there is no horizontal asymptote. So we're going to see how this looks with our limits here. All right, so now memorizing these patterns have worked for us thus far in Algebra 2 and Precalc. So we know we can just memorize these patterns. I just told you it's going to be the ratio of the lead coefficients, and that's how it works out. But the cool thing is we can now use limits to get a more analytical approach, and we can use limits to confirm why this works. So here's what we're going to do. So now in Precalc, in calculus, you have to show your work. So this is sort of that pre-calculus moment where I'm going to show you what that looks like, and we'll look at that here. So what it looks like is we are going to divide every term by the highest power of x in the denominator. This is important, in the denominator. And then we're going to use the following rule here, that the limit of a reciprocal function at positive or negative infinity is going to be 0 if the limit as x goes to infinity of 1 over x, or the limit as x goes to negative infinity of 1 over x is 0. So if it ends up, we get a function that goes out to 0 on both sides. Or we can continue anything where we can get 1 over x to some power is going to be 0. So this rule is going to help us out here. So here is what we're going to do. So the limit as x goes to negative infinity, looking at this function is bottom heavy. So it has a horizontal asymptote and limits follow asymptotes. So we can expect this to go to 0, but how can we prove this? So now what we're going to do is we are going to divide every term by the highest power of x in the denominator. So this is just our method that works. So that means x squared. We're going to divide everything by x squared. So this is going to be x over x squared plus 3 over x squared over 2x squared over x squared minus x over x squared plus 1 over x squared. Now we're going to simplify anything that we can. So this becomes 1 over x. This becomes 3 over x squared. And then over 2 minus 1 over x, because the x is reduced, and then plus 1 over x squared. So now using this corollary, anything that is 1 over x or some number over x, when we take the limit at positive or negative infinity, it is going to be 0. So the cool thing about limits is you can do direct substitution sort of piece by piece. So now we're going to say, all right, the limit as x goes to negative infinity of 1 over x, based on our corollary, that is 0. All right? The limit as 3x squared goes to negative infinity, well, that fits our corollary. That is also 0. So this is 0 plus 0 over, there's no x to plug in. We're kind of envisioning putting infinity in here. So there's no x here, so that's 2. Okay, as I plug in negative infinity in this 1 over x, that's going to go to 0 as well. So this would be minus 0, and then we get a plus 0. This all simplifies down to 0 over 2, which gives us a limit of 0, which is what we could expect. So this is how we can analytically show, not just guess within behavior rules, but we can actually show that this works. So let's look at 1 or 2 more examples before we finish up. All right, the next one. So for number 6, limit as x goes to positive infinity of this rational function 2x squared plus x plus 3 over x squared minus 9. So what we expect here is that This, when we think about the degree, this is equal. And so this means that our horizontal asymptote should be at, take the ratio of our lead coefficients, 2 over 1, it should be at 2. So in terms of asymptotes, I should expect the limit to follow that. I should expect the limit to come out to 2. Well, let's see if we can get that to happen here. So, all right, our rule is we take the highest degree of the denominator and we divide everything by it. So that makes this the limit as x goes to infinity of 2x squared over x squared plus x over x squared plus 3 over x squared all over x squared over x squared minus 9 over x squared. All right. So then next up, now we're going to simplify this down. So this becomes the limit as x goes to infinity of, let's see here, the 2x squared over x squared just becomes a 2 plus 1 over x plus 3 over x squared all over 1 minus 9 over x squared. If just memorizing a corollary, memorizing a rule that that those values go to 0 doesn't work for you, well, let's think about if I were to think of infinity as a massive number. As I place a really large number in for 1 over x, 1 over a really, really large denominator is going to be a number that gets closer and closer to 0. It's essentially going to be tiny, non-existent. And so that means that this term, when we actually evaluate at infinity, the 2, we can't do anything with that. It comes along because there's no x there. That 1 over x term, that's going to, as we go further and further out to infinity, that term's going to go away. It's going to go to 0. Same with if I take 3, divide it by some massive number, 100 million squared, that's going to go to 0. Over 1 minus another 9 over a massive number also goes to 0. So that makes this limit 2 over 1, or what we expected, it makes our limit come out to be 2. So this confirms for us here that when we have a horizontal asymptote and the limit follows that, we need to take the ratio of our lead coefficients. All right, let's do one more. All right, so then next up, we've got the limit as x goes to negative infinity of x cubed minus x squared plus 7 over x squared plus x. This is top heavy, so we would expect this to not have an asymptote, and so that's usually where it goes at infinity. It's going to diverge to infinity or negative infinity, but we don't know which one yet. So we're still going to apply our method and see what happens. So let's start. Our highest degree of the denominator is x squared. So we're going to continue our limit. We do need to type or copy this limit notation. And then we're going to divide everything by x squared. So we get x cubed over x squared minus x squared over x squared plus 7 over x squared. And we have x squared over x squared plus x over x squared. That part's probably the most tedious in this process. Now let's cancel out what we can. All right, x cubed divided by x squared, that just becomes x, and then minus x squared divided by x squared is 1, plus 7 over x squared. Then we get 1 plus 1 over x. So now looking at this, any of those terms that have fractions, so those are all going to go to 0 like we found. The numbers are going to stay, but we have something new here. We still have an x. There's no fraction. There's no nothing here. So as we work this through, let's think about, so I'm now going to evaluate my limit at negative infinity. So if I think about plugging negative infinity in for x, negative infinity is not a number we can actually plug in, but we can think about the general behavior. That number on the top is going to be some very large negative number that we could represent with negative infinity, minus 1, and then plus that 7 over x term at negative infinity, 7 over a massive number squared is still going to go to 0. We're not used to seeing this. This is kind of crazy. On the bottom, we have 1 plus, and then that 1 over x term is also going to go to 0. Here's the thing. Negative infinity minus 1 is still a really big negative number. It's not going to change it. We still represent that with negative infinity. So that means all of those numbers, when they combine to make this negative infinity. So remember, this is not an actual number, but this is describing the behavior. This graph is heading toward negative infinity as x heads toward negative infinity. So it's going downward. All right, so that is it with limits at infinity. If you have questions, be sure to reach out to me, come to office hours, come to check-ins, and we can get you caught up and hopefully help you from there.